G'day everybody. In this lesson we are going to look at two applications of definite integrals. We've seen recently how we calculate definite integrals, how we use them to find the area between a curve and the x-axis. By finding areas, we can work through these two other problems today. We're going to do some work finding the area bound by two graphs. In the second half of this lesson, we're going to use areas to calculate the average value of a function. First of all, looking at the area bound by two curves, here's a statement about how we calculate the area. We've got two functions g and f. They overlap, and they might overlap in between two values of x, a and b. And you can see where a and b are used in our definite integral. Here's a diagram about what that might look like. We can see here we've got our function g is above function f, and that's the reason for this statement here. So whatever function has a higher value for that interval, it's going to be the integral of g minus the integral of f, which is really like taking all of that area below g and then subtracting all of the area below f in between these 2 points a and b. Now usually a and b are the values of x where the curves intersect, particularly if we word the question like this, an area bound by two curves. But we don't have to necessarily find the area between intersections. We can find the area that lies in between two curves and between any two values of x, a and b, whether they intersect or not. This diagram here is just to show you that the integral here would be the same for both of these functions, even when the x-axis is passing through that area. We saw in a recent lesson when we're calculating areas below curves using definite integrals, it's really important to know whether the area lies above or below the function. But in the case of finding the area bound by two graphs, we really don't need to worry about where the x-axis is. A couple of pointers. As always, when you're calculating definite integrals and areas, always look at a sketch, just checking where those areas are. It will show you also which function is higher, which function is lower, roughly where those intersections are. Importantly, it might also show you that there is more than two intersections, and in that case you would need to divide your calculations up into more than one part. And remember that the position of the x-axis is really not important. We're going to do an example. I'm actually going to use CAS Calculator to highlight our example today. So we're going to find the area bound by the curves f of x and g of x. You can see on the screen here which function is which. We might be able to guess which function is going to have the higher value in this case, but it really doesn't hurt to have a look at a sketch. It could actually be either. First of all, I'm going to use the calculator to define my functions f and g. Now I can use them in the calculator wherever I need to. I'm looking here at the graphs of f and g. What I'm observing here is the red function. That's my g of x curve. So for the interval where there is a bound area, g of x is the higher or the greater of the two functions. Of course, the blue function is our curve for f of x. And I can also see roughly where the curves intersect. So in this case, I am going to find the area bound by the two curves from the points of intersection. I'm going to use the calculator to solve where those 2 points are. I could also use the graph, but in this case I'm going to solve when the functions are equal to each other for x, and that shows me that there are two intersections, one where x equals -2 and the other intersection where x equals 4. We saw in our graph a moment ago the red function g was the higher of the two functions, so I'm going to find the definite integral of g minus f between the 2 points x equals -2 and x equals +4, and that tells me that the exact area that's bound by those two functions is 72. I'm going to also use the calculator in a different way. We're going to use the menu on the graphing page of the calculator. Here we can see our two sketches. If we use the Analyze Graph menu, we'll find there's a function for calculating the bound area, or the bounded area. When you choose that function, the calculator is going to ask you for 2 points to use as your x equals a, x equals b. It will call them the lower bound and the upper bound. And then you can select either the points of intersection, or you can select other points if they're applicable. Here you can see I've selected the 2 points where they intersect. I just had to use the touchpad to click on those intersections, and you can see it's shaded the area that's bound by the two functions, and it's giving me the area which is 72. So that's calculating areas bound by two functions using definite integrals. The second part of this lesson, we're going to answer the question, how do we find the average value of a function? I'm going to use this particular example. Let's say we've got a function, it's another parabola, but I'm interested in the average value of the function for the part of the graph that is shown. So we can see here we've got the function from x equals 2 to x equals 6. Let's think about 3 questions just to get us warmed up. Let's talk about the minimum value of the function. What could that be? What would be the maximum value of the function? And we'll have a little bit of a think about what would the average value of the function be. So from the graph, we can see at either of these two endpoints, the maximum value of the function is 10. At the turning point of the parabola, we can read the minimum value of the function is equal to 6. So our key question, what about the average value of the function? Obviously we expect that it's going to lie somewhere between 6 and 10. Does it lie exactly halfway? What we're going to find out is no. As you can see, the function has a bit of a curve to it. So halfway would be 8, but we can see that a lot more of the time between those two values 2 and 6, the function is actually below 8, and for a smaller period of time the function is above 8. So it doesn't really make sense to say that our average value is equal to 8. This is a bit of a definition about how we think about the average value. We can see our curve here on the left. Just reading here, when the area of the rectangle is equal to the area under the curve, the height of the rectangle will represent the average value of that function. So just on this screen, we're actually going to play with the height of that rectangle, and we're going to change its height and see if we can estimate an average value. So if I adjust this rectangle, obviously that's right up the top. I would like the area of this rectangle to be equal to the area that's under the entire curve, between the curve and the x-axis. So I've already discussed that I think 8 is too high. I think there's only a little bit of area above the rectangle, and we can see this dip here below the top of the rectangle, I really want those areas to be equal or to even out. So I'm going to lower that a little bit. Might put it about there. And so this gives me an indication. I'm sort of thinking that this little pocket of area, this little pocket, or these two little gaps might be equal to this pocket that's in between the parabola and the top of the rectangle. So now I'm thinking that maybe my area of the rectangle is pretty close to the area under the curve. And I can see that the height of the rectangle is about 7.25. So that's going to be my guess. I'm going to guess that the average value of the function is 7.25. So this diagram shows the actual average value, and we're going to have a quick discussion about how we can use calculus to determine what that exact average value is. First of all, I'm interested in the area under the curve, the purple section. And that's where our definite integral comes in. So the area below the curve is equal to the definite integral of the function from x equals 2 to x equals 6. Now that I've got that area, I'd like to think about the rectangle as having that same area, and I'm thinking about what would the height of that rectangle be. If I divide that area by the width of the rectangle, so x equals 2, x equals 6, I've got a width that's equal to 4. So 1/4 of that area, or that area divided by 4, that's going to give us the height of the rectangle, which is our average value. So in this case, by taking the area under the curve, dividing it by the width of the rectangle, that's going to give us the average value of the function, which is 22/3, which is 7 1/3 or 7.33, pretty close to my guess of 7.25, but the exact average value is 22/3. So let's just summarise and write our average value as a bit of a definition. We can see here we've got another curve over here. We've got a function, the blue area below that function is equal to the area of the grey rectangle. We're interested in the average value of the function, the blue function, between x equals a, x equals b. Once we've found that those two areas are equal, or once we've used that fact, this leads us to a definition or a formula for the average value of a function between 2 points a and b. So here's our definite integral, the integral of the function from a to b multiplied by 1 over the width of that interval. In other words, 1 over b minus a. So there's our formula for the average value of a function. So in this video, we've used definite integrals for two types of problems. We've used it to find the area bound by two graphs. We also did some work on our CAS calculator in two different ways, finding that area. And we've had a look at what it means to find the average value of a function. And we now have a formula for calculating that as an exact value. If you've got questions from this lesson, please write them down, bring them to class, and as usual, complete the Google form, log your attendance, and there'll be a few questions there for you to check your understanding. Thanks very much.